Deep inside the copper wiring of your walls, the alternating current halts. The 60 Hz sine wave flatlines. In exactly 14 milliseconds, the electromagnetic field within your transformer collapses. The furnace fan dies. The ambient temperature of your living room begins an immediate mathematical descent. We treat a winter power outage as a temporary modern inconvenience. Physics treats it as a thermodynamic equalization. The heat will leave your body, move through the drywall, and vanish into the freezing atmosphere. You are leaking energy. Last winter, as an Arctic front paralyzed the fragile electrical infrastructure of rural Montana, a 74-year-old man insulated himself against this thermodynamic inevitability. For 3 consecutive nights, with zero electricity, zero natural gas, and zero firewood, his home remained entirely habitable. His total financial expenditure for this thermal defiance was exactly $1. And when his neighbor eventually crossed the snow line to ask how he survived without freezing, the man simply smiled and pointed to a mundane, unremarkable object resting in the corner of the room. A standard bag of barbecue charcoal. Do not look away assuming this is a parlor trick, because what this man deployed is a fundamental principle of survival that millions of human beings in developing nations have utilized for decades. It is a precise thermal mechanism that off-grid survivalists have quietly perfected. It is a protocol that the average suburban family could initiate tonight to drastically sever their heating costs or survive a total grid failure without suffering hypothermia. My identity is irrelevant. What matters is the mechanical truth you are about to absorb. By the end of this lecture, your perception of a simple bag of charcoal will be permanently altered. You are not here for theatrics or digital hype. You are here for practical economic realities, the brutal mechanics of energy consumption, and the kind of common-sense physics that human beings passed down for generations before we outsourced our survival. We deal in reality. Let us examine heat. Real biological heat. When the external temperature plummets to -10 degrees, the power grid fails, and a family is sitting in the dark, wrapped in every synthetic fabric they own. The psychological response is panic. Most people have no protocol. This is not a failure of intelligence. It is a structural failure of modern conditioning. The contemporary human has committed a catastrophic evolutionary error. We have constructed our entire physiological safety around closed-loop technological systems that we do not understand and cannot control. Electric space heaters, forced air gas furnaces, and wireless smart thermostats are brilliant miracles of engineering until the moment the connection is severed. When the grid stops, the people freeze. Literally. Enter carbonized wood. But before we deconstruct the physics of this mechanism, a non-negotiable biological boundary must be drawn. We are discussing standard, commercially available outdoor charcoal. Igniting this exact material inside a sealed architectural envelope without calculated, intentional ventilation is a lethal miscalculation. Carbon monoxide is invisible. It is completely odorless. When inhaled, it bonds to the hemoglobin in your bloodstream with an affinity 200 times greater than oxygen, suffocating your cellular structure from the inside out while your lungs continue to passively expand. It will kill you. Therefore, every single variable we discuss regarding indoor charcoal use hinges on strict safety protocols, absolute ventilation, and controlled airflow. Ignore the physics of ventilation, and you convert a survival tool into an execution chamber. Pay attention to the details. A standard bag of charcoal, the exact kind you can purchase at any corner gas station, grocery store, or hardware store, costs between $1 and $3. Yet, a single pound of this material, when subjected to proper combustion constraints, generates a staggering volume of thermal energy for an extended duration. We are not discussing the rapid, chaotic, and inefficient oxidation of raw firewood, which flares up and vanishes in 20 minutes. We are talking about slow, manageable, sustained heat that can dictate the temperature of a space for hours. Consider the macroeconomic environment for a moment. Home heating costs have violently accelerated over the past 5 years. Natural gas prices fracture and swing wildly based on geopolitical conflicts and global supply chains. In specific regions, baseline electricity rates have surged by 30, 40, or even 50%. Against this volatile backdrop, a $1 bag of charcoal resting on a shelf in your garage ceases to be a summer leisure item. It transforms into an asymmetric asset. It is not meant to replace your primary heating infrastructure. It is an emergency thermal battery. It is a fail-safe that could genuinely protect human life on the coldest, darkest night of the year. What the modern citizen fails to realize about charcoal is its molecular density. It is, fundamentally, concentrated kinetic energy. When raw cellulose and lignin are subjected to extreme thermal stress in an oxygen-starved environment, a chemical process called pyrolysis occurs. The moisture trapped within the cellular walls vaporizes. The volatile organic compounds boil away. What remains is a skeletal matrix of nearly pure carbon. And carbon is relentless. Carbon burns hot. Carbon burns cleanly compared to raw timber. Carbon burns long. The metallurgists of the Bronze Age utilized this exact thermal reaction to melt copper. Industrial-era blacksmiths forged steel on its embers. Modern survivalists quietly depend on its efficiency today. The caloric density packed into these blackened fragments is genuinely staggering, especially given its global ubiquity and near-zero cost. You can acquire this stored energy in almost any hemisphere at any time of year for mere pennies. But a mechanical question inevitably arises. How does one single dollar of carbon actually sustain human life through a freezing night? What is the specific setup? We are going to dissect this operation down to its fundamental physics, because the method matters equally as much as the fuel. You can possess the correct material and still execute the process with fatal incompetence. The individuals who have mastered this mechanism, the off-grid homesteaders, the disaster response technicians, the populations living in regions where the grid is a fragile, rolling suggestion, do not guess. They follow a strict, calculated approach. That specific protocol is what transforms a cheap bag of briquettes into a sustained, all-night thermal engine. We will systematically cover the chemical variations of the fuel, the container geometry, the critical airflow equations, the non-negotiable safety parameters, and the historical precedents of how this exact method has preserved life during modern grid failures. First, we must correct a cultural misunderstanding. In the comfortable, manicured enclaves of modern suburbs, charcoal is synonymous with recreation. It conjures images of summer patios, cast aluminum grills, and the sharp, volatile scent of aliphatic hydrocarbon lighter fluid on a Saturday afternoon. But if you exist in a rural landscape, or a developing nation with fractured electrical infrastructure, charcoal represents a stark biological necessity. It means the preservation of core body temperature. It means boiling water when the grid collapses. It means survival in the most literal, unforgiving sense of the word. The cognitive gap between these two worlds, between those who view this carbon as a culinary luxury and those who view it as a lifeline, is vast. We will close that gap right now. The primary variable is the fuel itself. Not all charcoal shares the same chemical profile. In the American consumer market, you will encounter two dominant forms. The first is the briquette uniform, compressed, geometric blocks found in nearly every grocery store. These are an engineered composite. They consist of charcoal dust, raw coal, starch binders, and occasionally chemical accelerants designed to speed ignition. The second form is lump charcoal. This is pure, raw hardwood, charred down to its skeletal carbon base without a single synthetic additive or binding agent. It is irregular, chunky, and structurally natural. Because it is. For the purposes of emergency indoor heat management, lump charcoal is the superior biological choice. It achieves a higher combustion temperature. It burns cleanly. It does not release the toxic, synthetic fumes associated with chemical binders. However, lump charcoal is slightly more expensive and sporadically stocked in small rural hardware stores. Briquettes, conversely, are ubiquitous. You will find them everywhere. And if briquettes are your only available fuel source, they will absolutely suffice, but they require a strict sequence of execution. You must ignite them outside and wait for the initial chemical burn-off phase to conclude. This off-gassing period is the dangerous phase. You cannot bypass it. You must wait until the briquettes are fully ignited, glowing with a deep, radiant orange and completely encased in a shroud of white ash. That white ash is the visual confirmation of clean, stable combustion. Now, we address the physical apparatus. The charcoal is merely half of the thermodynamic equation. The other half is containment, thermal radiation, and the precise management of oxygen flow. This is the exact intersection where desperate people make fatal errors when improvising heat in a blackout. The human instinct during a freezing emergency is to escalate. They assume a larger fire guarantees greater warmth. They pile on raw fuel, inadvertently restrict the oxygen intake, and trigger a smoldering, incomplete combustion reaction that produces massive volumes of lethal carbon monoxide instead of radiant heat. They suffocate the reaction. They manufacture poison. That is the wrong approach. The correct approach relies on controlled, metered combustion. It requires a minimal fraction of fuel, a precise oxygen draft, the correct containment vessel, and strategic placement. Let us define the hardware. For the containment vessel, the most universally applied and efficient tool among off-grid specialists is profoundly simple. It is a standard terracotta clay flower pot. Specifically, this mechanism relies on a standard terracotta flower pot. You place a large terracotta vessel on the floor. You nest a second, smaller terracotta vessel inside of it. The empty geometric volume between the two clay walls creates a thermal trap. You elevate the inner pot slightly using a small steel rack or a few common bricks to permit ambient air to flow underneath. You place the carbon fuel strictly inside the inner vessel. There is a profound reason for using baked earth. Materials scientists at the Fraunhofer Institute have extensively documented the high specific heat capacity of fired clay. If you place burning charcoal inside a thin steel bucket, the metal conducts the heat instantly and dissipates it violently into the air. But terracotta is different. Fired clay absorbs thermal energy, stores it deeply within its dense crystalline structure, and radiates it outward in a steady, slow, horizontal wave. Clay is a natural thermal battery. It captures the violent chaos of combustion. It releases a controlled, enduring warmth. Alternative vessels can be substituted. A small cast iron hibachi grill. A punctured steel coffee can. The exact container is secondary to the physical principle it must enforce. The vessel must contain the carbon securely, channel the oxygen precisely, and force the thermal radiation laterally into your living space, rather than allowing the heat to escape vertically toward the ceiling. This brings us to the airflow equation. Fire is not an object. It is an active, breathing organism. It demands respiration. If you starve the vessel of oxygen, the charcoal smolders in a state of incomplete combustion. It generates massive, lethal concentrations of carbon monoxide and virtually zero usable heat. If you overfeed the vessel with oxygen, the carbon oxidizes frantically. It exhausts your fuel supply and spikes the room temperature for 30 useless minutes before dying. The objective is a metered, respiratory draft. Small holes at the base of your container pull cold, oxygen-heavy air inward. Basic thermodynamics dictates that the heated exhaust will rise, creating a continuous vacuum that pulls more fresh air through the bottom. The cycle becomes self-sustaining. This is elementary fluid dynamics. Get this right, and the heat lasts until dawn. You are manipulating physics. The volume of fuel required for this reaction defies human intuition. The modern brain expects a roaring, massive bonfire to survive the cold. Logic dictates precision. Off-grid specialists consistently deploy a remarkably small payload, exactly 6 to 10 standard briquettes, or a single, small handful of lumped charcoal. That is all. The sustained warmth does not come from igniting a massive pile of fuel. The efficiency is structural. It comes from the thermal trap you just engineered. This is precisely why a $1 bag of charcoal holds exponentially more heating sessions than a panicked homeowner expects. I am going to pause the timeline of this setup to address ventilation. This is the single most critical variable in the equation. When carbon burns, it off-gasses carbon monoxide. If you place this terracotta mechanism inside a hermetically sealed bedroom, the atmospheric chemistry of that room will slowly shift. The carbon monoxide will pool. It will displace the oxygen. It will terminate your life while you sleep. This is not hyperbole. It is a documented forensic reality. People have died desperately trying to stay warm because they ignored this step. You must intentionally breach the seal of the room. Crack a single window by a fraction of an inch. Open the interior door slightly. You must establish an intentional, physical pathway for fresh oxygen to flow inward and for toxic combustion exhaust to drift outward. This controlled draft will not bleed away your baseline heat. It will keep your blood oxygenated. Furthermore, You will acquire a battery-powered carbon monoxide detector. You will place it inside the room. You will turn it on. This is not an optional accessory. It is a biological mandate. The charcoal, however, is merely the heat core of a much larger thermodynamic strategy. When the power grid fails, your immediate panicked instinct will be to attempt to heat your entire house. Suppress that instinct immediately. Your modern house, with its vaulted ceilings, open hallways, and sprawling square footage, is an absolute thermal sieve. It will drain the heat from your terracotta battery instantly. You must isolate a single zone. Select the smallest room your family can comfortably occupy. Choose an interior room. An interior room shares fewer exterior walls with the freezing environment outside. Less surface area exposed to the winter means a drastically lower rate of heat loss. Once you have selected your thermal bunker, you must seal its perimeter. Wedge a thick draft stopper or a rolled-up bath towel firmly under the base of the door. Stuff fabric into the microgaps around the window frames. Hang heavy blankets directly over the glass. Architectural glass is a thermal void. It offers virtually zero resistance to the freezing temperatures outside. A thick, moving blanket draped over a window immediately halts the kinetic transfer of heat. You already possess these textiles in your closets. You are taking a standard, vulnerable bedroom and converting it into an insulated thermal pocket. Place your clay mechanism in the center of this insulated pocket. Ensure your ventilation pathway is open. Activate your carbon monoxide detector. Ignite the 6 briquettes. Because you have minimized the room's total air volume and trapped the thermal radiation, the ambient temperature will rise and hold in a way that feels almost impossible given the tiny fraction of fuel you are consuming. Small fuel, small space, massive compounding efficiency. Now, introduce the final heat source. The human metabolic engine. The average adult human radiates approximately 100 watts of continuous thermal energy at rest. Put 3 living bodies in a heavily insulated, sealed room, and you have essentially installed a biological space heater. Insulate those bodies in sleeping bags, heavy quilts, and thick wool layers. The human body evolved to generate its own heat. Your clothing is merely the barrier that traps it against your skin. The charcoal mechanism does not have to heat the people. It only has to maintain the baseline temperature of the surrounding air, reducing the metabolic workload on your body. Under these strict parameters, a handful of charcoal will realistically maintain a survivable baseline temperature throughout an entire winter night. It will not mimic the luxurious 72-degree artificial climate you are accustomed to. You will not be comfortable, but you will not succumb to hypothermia. It is warm enough, and when the external environment turns lethal, warm enough is an absolute victory. The economic reality of this system is undeniable. We are watching global energy markets fracture. We are watching utility rates decimate household budgets. A winter grid failure is not merely a biological threat, it is a catastrophic financial event. Emergency hotel stays, ruptured water pipes. The downstream costs of structural freezing easily measure in the thousands of dollars. You can assemble this entire fail-safe protocol, the clay pots, the bag of charcoal, the carbon monoxide sensor, the towels, for less than $20. It is an asymmetric investment against total systemic collapse. For 200,000 years of hominid evolution, the generation of heat was a daily, active responsibility. Our ancestors understood the exact physical mechanics of insulation, fuel, and fire. The modern industrial era stripped us of that physical competence. We outsourced our survival to centralized utility monopolies and subterranean gas lines. We traded our autonomy for a thermostat dial. And that arrangement works beautifully right up until the moment the grid is overwhelmed, the wires snap under the weight of accumulating ice, and the repair crews cannot reach you. In the dark, the people who survive are never the ones with the largest bank accounts or the most expensive gear. They are the ones who understand basic physics. They are the ones who built a plan before the temperature dropped. Here is your directive. Tomorrow, go to a local hardware store. Purchase a small bag of pure lump charcoal, 2 terracotta pots, and a battery-operated carbon monoxide sensor. Gather a heavy blanket and a draft stopper. Place all of these items in a designated corner of your garage. Leave them there, because eventually, the 60 Hz sine wave will flatline. The electromagnetic field inside your neighborhood transformer will inevitably collapse. The furnace fan will die. And when the copper wiring in your walls finally goes completely silent, you will strike a match and you will command the thermodynamics of the room.